Hello, welcome back. This is the part three of the lecture. At the end of the part two, I was talking about expected value. And I defined the expected value of some function g of capital X at capital Y for the discrete case and continuous case. And you can see this is a direct extension of the definition for expected value of gx. Uh, when you have a single variable. So let us now look at an example. Find the center of gravity of the triangle with vertices 0, 0, 1, 1, and 1, 0 with uniform density. Of course, from geometry, we know where the center of gravity of a triangle lies. We will find the same thing using this idea here, the expected value. You may recall that I explained when I was explaining the expected value of random variable x. I explained that it is the center of gravity of the distribution of that random variable, center of gravity. Similar, the same idea can be extended to two variables, bivariate case also. If x and y are two random variables, then suppose it has a certain density function, then the center of gravity of the volume that you are considering under the density function will be at the point expected value of x, comma, expected value of y. So the x coordinate of the center of gravity will be expected value of capital X. Y coordinate of the center of gravity will be expected value of capital Y. So that's what we are going to find out here. Uh, of course, in this case, what we want is the center of gravity of a triangle. Therefore, we will look at a flat density rather than some other curvy density. So we want to look at a flat density. So therefore, we will consider a uniform distribution over this particular triangle, considering this particular triangle as the support. So we will consider this situation here. This is 0, 0 point, this is 0, 1, and this is 1, 0 point. So this is actually the surface uniform distribution over this particular triangle. So what should be the height of the triangle, height of the joint density? We know that the area under the joint density should be equal to 1. But the support here is going to be just this triangle 0, 0, 1, 0, and 0, 1, given by those 3 points. And that is actually half of the rectangle, right? The square 0, 1, 1, 0, and then 1, 1 square, right? Half of that. Therefore, the area of the support is half, one half. So the surface is going to be above that, joint density surface is going to be above that, and it's uniform. So the height should be then equal to 2, so that the area under the surface becomes 1. So therefore, our joint density function will be equal to 2 when x and y are satisfying this condition, right? So y, in this case, less than or equal to x, but x is less than 1, y is greater than 0, right? So we want to find out the expected value of x and expected value of y for this particular density, uniform density. Right. So expected value of x, in this case, when you're finding the expected value of x, I'm looking at a particular g of xy value, but g of xy in this case is equal to uh, g of x comma y will be equal to just x. Right. So expected value of x is going to be integration of double integration of g of xy, in this case just x, times the density function 2, and then dx dy or dy dx, depending on what, uh, with respect to which variable you are going to integrate first. So I'm going to integrate the whole, we have to integrate over the whole support, of course. Therefore, I'm going to consider this vertical stripe, vertical as parallel to the y-axis first, and thereby integrate with respect to y from here to here, and then to cover the whole area, I will change x from 0 to 1. So therefore, because I'm integrating with respect to y first, y values will go from 0 to, if you are considering a particular x value here, at that point, y is equal to x. So 0 to x, right? And then x will go from 0 to 1. So that will be the expected value of x. And similarly, when you're finding the expected value of y, my g of xy now becomes capital Y. So expected value of y will be now integration, again double integration, y times 2, that is 2 is the joint density, again dy by dx. But now this is, if I'm using the same method to cover the support, I will be integrating with respect to y. So y will be going from 0 to x, but x will be going from 0 to 1. Right. So these are the two expressions I have to integrate. But here you can see that when you are integrating first with respect to y, this thing will be regarded as a constant. So you will have then 2 times x times y, and then you put the limits and then integrate with respect to x. But here when you are integrating with respect to y, y square divided by 2 will come here, and then 2 will cancel out, and then put the limits and then integrate with respect to x. So therefore, that you will get two different answers for the expected value of x and expected value of y in this case. Right. So expected value of x, right, integrating 2x with respect to y from 0 to x first, and then integrating with respect to x from 0 to 1, you get 2 over 3. And expected value of y, you are integrating 2 times y with respect to y first. Y goes from 0 to x, and then x goes from 0 to 1. But now the answer is 1 over 3. So therefore, the point of center of gravity will be, x coordinate of that will be equal to 2 over 3. Y coordinate is equal to 1 over 3. So that's what I have shown here in the picture. That point here, x equal to 2 over 3, y equal to 1 over 3. And this is the center of gravity that we know from geometry also. Right? So that's from geometry, what we know is that it's going to be the half of this distance, and this again 1 over third distance from this point. So that's what we learn from geometry. But here we find out that x coordinate is 2 over 3 and y coordinate is 1 over 3, which gives the same point. So that is a good example actually about expected value of x and its applications and so. So now let us look at another example regarding the expected value. In this case, find the average distance. This is coming from David and Co's book. Actually, previous one also from that from the textbook, David and Co's book. Find the average distance between two random points on the interval of unit length. Use simulations to check the answer. Right. So take any x value and y value where x is between 0 and 1. X is uniformly distributed, and then y is also between 0 and 1 uniformly distributed. Then the distance between those two will be the absolute x minus y, absolute value of x minus y. So what we have to do is to find out the expected value of the absolute value of x minus y. So let x and y be the 2 points, right? Let x be x and y are IID uniform 0, 1. IID means identically distributed. That means both have the same uniform distribution. ID means independently identically distributed. Independent. First I is independent. Second I is identically. Then D is distributed. So therefore, if x and y are independent, actually, we haven't discussed independence yet. But when you do that, you will see this. The joint density is equal to the product of the densities. Each density is a uniform density. So in 0, 1, so the value of the density is 1. Value of the density of y is also 1. Therefore, the joint density is just 1, where x and y are independently between 0 and 1. So therefore, the joint density is just 1. So we are the support here is the rectangle, square actually, square from 0 to 1, 0, 0, 1, 1, 1, 0, 0, 1 points. So what we want is gxy, right? The function of interest is equal to absolute value of x minus y. So we need the expected value of that gxy, right? So we are looking at that. So naturally, it has to be the integration of our g function times 1, where 1 is the joint density with integration with respect to x and y. But in this case, both x and y are going to be changing from 0 to 1, right? There is no restriction connecting x and y, right? Independently, x and y are changing between 0 and 1. Right. So therefore, that's what we have to look at. So we will first look at this quantity and then look at this quantity. But here you can see that absolute value of x and y, x minus y will be positive in some situations, will be negative in some other situations. When x is equal to y, then this will be 0. Otherwise, when y is less than x, this quantity will be positive. On the other hand, if y is greater than x, this will be negative. Therefore, we can define this in this range, we can define x minus y to be like this, right? Absolute x minus y is equal to y minus x if x minus y is negative. On the other hand, absolute x minus y is equal to just x minus y if x minus y is positive. Right. So x minus y is negative when y is less than x. Otherwise, this is positive when x is greater than y. So therefore, we will break this interval into two parts and then take the corresponding function when you are integrating absolute value of x minus y with respect to x. Right. So therefore, this is how we break it down. Right. So this will be y minus x. When x is changing from 0 to y, this will be y minus x. Right. So x is, so in that case, this is positive. And then on the other hand, when x is changing from y to 1, x minus y will be positive in that case. So therefore, this is the quantity that we have to look at when you are integrating this part only, that this first integration part. Right. This part here, and then we have to integrate with respect to y after that. So we will get this one first. You can see that when you integrate with this thing and put the limits in terms of y's, you are going to get an expression in terms of y. Then you have to integrate this whole thing from 0 to 1 with respect to y. Right? So integrate that thing with respect to y from 0 to 1. Then you get the answer 1 over 3. Right. So therefore, average distance of points between x and y when you are selecting x and y randomly is going to be 1 over 3. Right. So we have been asked to check the answer using a simulation. So I'm going to consider about 100,000 simulations here. So what I'm going to do is get 100,000, n is equal to 100,000, 100,000 random numbers from 0 to 1 interval and check those are x, and then take another set of random numbers, again 100,000 in the same distribution. Then just consider now I have actually pairs. I can consider pairs, therefore I can consider x minus y, and then take the absolute value. So I'll have 100,000 x minus y values where x's are random uniform numbers, y's are random uniform, right? So then once you get the distance, you can find out the mean distance. And this is what I got, 0.33 in this particular simulation. If you do another 100,000, your answer might be slightly different, but again, close to zero point 0.3 because the theoretical answer is 1 over 3. So the theoretical answer is 0.3333, right? So what we have here is very close to that, up to uh, two decimal places. So that's how you check the answer in this particular case. Right. So that is the end of discussion for the moment about the expected value of some function g of xy. Now we will look at the final part for today's lecture. We will consider the independence, right, of two random variables. Remember, we already know how to define the independence of two events, right? If A and B are two events, we say usually we start with the definition start with the conditional probability, right? If the conditional probability of event A given event B is the same as the unconditional probability of event A, in that case we say A and B are independent. Right? The same thing is equivalent to saying the two events A and B are independent if and only if the probability of the intersection of A and B is equal to the probability of A times probability of B. That is another way to define the independence of two events. Right. Now, how do we define the independence of two random variables, say X and Y? For random variables, actually, you can consider large number of events, right? Not only one event, right? If you're talking about A and B events, that's you have only one intersection to consider there. But if you consider random variables, you can consider large number of events and their intersections. Then for each of those intersections, this condition have to be satisfied. But what we can do is actually, but in particular, if the random variables x and y are discrete, we can consider a particular set of events rather than all the events, because all the events can be written down in terms of these events. Right? So therefore, let's consider x equal to simple x event and y is equal to simple y for any simple x and simple. So for the moment, let us fix a simple x value and simple y value. Consider the event capital X equal to that given x and capital Y is equal to that given y. So if this condition is satisfied for these two events, then we can take another simple x and another y and then check this condition for that. And so if the condition is satisfied for all possible x's and y's, right, then we would say that random variable x and y are independent. Right? Then, of course, this condition will be satisfied for any other event as well. We can prove that. Right? So, therefore, it is enough to consider events of this form, right, for all possible values of capital X and all possible values of capital Y. So to say that the random variables x and y are independent, we require all such events of pairs to be independent. Right? So therefore, we say two random variables x and y are independent if the probability that x equal to x and y equal to y is equal to the probability that x equal to simple x times the probability y equal to simple y, like this for all possible pairs of x and y. If this condition is not satisfied for at least one pair of xy, then x and y are not independent. Not independent. Right? So usually it will be easy for us to prove that some two random variables are not independent than showing it is independent. But of course, to show that they are independent, we'll have to prove this for all xy possible xy pairs. So that is the definition of the independence of two discrete random variables. Discrete. For the discrete case, of course, you can define probability x equal to simple x, usually non-zero, and then probability y equal to simple y, non-zero. Right. But you cannot use this definition, this way to define the independence of two continuous random variables. Why? In that case, of course, whether or not, regardless of whether x and y are independent, this probability product will be always zero, and this will be always zero, and therefore, regardless of whether the two random variables are independent or not, this will be always true. Zero equal to zero, right? So therefore we cannot check whether the two random variables are independent in that case by using this definition. So therefore, instead of this definition, what we usually look at is the probability that x less than or equal to simple x and y less than or equal to simple. Those are the two events that we consider in that case. So the probability, that condition must be that we can consider that those two events in the discrete case also. But in the discrete case, considering this is much more easier. Right? So for continuous cases, what we look at is the two events x less than equal to simple x and y less than or equal to simple y. Right. So the random variables x and y are independent if and only if the probability x less than or equal to simple x and y less than or equal to simple y is equal to the product of those corresponding probabilities, which can be written in terms of the joint cumulative distribution function and marginal cumulative distribution function. So this is the joint cumulative distribution function of x and y evaluated at simple x and simple y. This is the product of individual marginal cumulative distribution functions at x and y respective. Right? So this is the suitable definition for the independence for two continuous random variables. Of course, this definition can also be used for the discrete cases, discrete random variables, but in that case, the previous definition would be much easier, right? Okay. Uh, Now, this definition, or this one definition, we can express the requirement in the continuous case also in terms of the density function, because this is one definition. If you differentiate both sides with respect to x and y, you will get this expression. Right? So if you differentiate this thing, then you get the joint density. And if you differentiate this thing with respect to x and y, because this is, in this case, this is only a function of x. When you're differentiating with respect to y, you can consider this as a constant, right? So d of dx, first you are taking this as a constant times the differentiation with respect to y, and then differentiation with respect to x will give you, in that case, this will be a constant. So this will be differentiation of this function with respect to x times this one. So that's going to be the density, the product of the density of each random variable. So this is actually easier than the expressing in terms of the cumulative distribution function. So we would say two continuous random variables are independent if and only if the joint density function can be written as a product of the two individual density functions. Or in other words, we can say if you can factorize the joint density into a product of two functions separately, one function of x, the other function of y. And of course, then there will be a constant, but that has to be the normal, normalizing constant, right? So therefore, usually the way that we express it is the joint density has to be equal to the product of individual marginal densities for the random variables to be independent, right? Now, let us look at an example. This is again from the book. This is example 3.7 in the book. Mary and John participate in a conference call set up at 10 a.m. The bivariate density of the times they join the group is given by this expression, right? So they may not join exactly at 10 o'clock. One person might be X minutes late, the other person might be Y minutes late, for example, right? So here where X stand for Mary and Y stand for John, minutes after 10 a.m. Right? So how late they are, I mean, in other words. Prove that Mary and John joined the meeting independently. Right. So in order to prove that they are joining the meeting independently, what you have to prove is that the corresponding random variables, capital X and capital Y, are independent random variables. So in order to prove that, we have to show that the joint density given by this expression is equal to the product of the marginal densities of X and Y respectively. And then it asks us to calculate the probability that John joins the group 2 minutes after Mary and check the answer via simulation. So first we have to calculate the probability theoretically and then check the answer via simulations. So let's first of all derive the marginal distributions. Now in this case, again, notice the domain, the support of the distribution is going to be, in this case, this is, it's not given here, but in this case, is x greater than or equal to 0, y greater than or equal to 0, right? X greater than or equal to 0 and y greater than or equal to 0. There is no restriction in terms of x and y together, right? So x and y can freely vary, but they have to be greater than or equal to 0. That's it. Right. So let's find out the marginal distribution. So in order to find out the marginal distribution of x, we have to integrate the joint density with respect to y. So y has to go from 0 to infinity. Right. So when you are integrating e to the power x, that part can be taken out because that will be considered as a constant. So this is integrated and put the limit, and then finally you get e to the power minus x. Similarly, the marginal density of y will be e to the power minus y. So you can easily identify that actually the marginal distribution is actually an exponential distribution with rate equal to 1, while marginal distribution of y is also exponential with rate equal to 1. And what we want is actually to show that the joint density is actually the product of these two. And in fact, it is coming in that way. We can easily see that this thing is the product of those two marginals. Therefore, that implies that capital X and capital Y are independent. Then to answer the second question, what is the probability that the John joins the group 2 minutes after Mary? Right. So the time that Mary comes is X, the time John comes is Y. So the question is, what is the probability that Y greater than X plus 2? Y greater than X plus 2, 2 minutes after Mary. Right. So we are looking at this particular probability Y greater than X plus 2. So then you have to integrate the joint density over the region satisfying X and Y satisfying Y greater than X plus 2, or you can say the same thing, Y minus X greater than 2. Right. So you have to integrate with respect to Y and X. So if you are integrating with respect to Y, you have to put the limit for Y. Right. So Y greater than x plus 2, right? In the region y greater than x plus 2. So therefore, and therefore y can go up to infinity. Therefore, y will be changing from x plus 2 to infinity. And then x, when you are integrating with respect to x can go from 0 to infinity. So therefore, the probability y greater than x plus 2 is given by this expression. And then we get this answer here, right? 0.067. That is the theoretical answer. Right. We can get the same answer by simulating, not the same answer, approximately the same answer by simulating. So for that, what we have to do is we have to simulate some exponential random numbers from with rate 1, and then from some wide and exponential random numbers with rate 1, and then see, take those as pairs, right? So you can take them as pairs, and then see in each pair how many y's are greater than x plus 2, and then find out the proportion of those observations. So therefore we can write down the command. So here also I'm looking at a very large number of observations, right? More than even 100,000 here. I think I wanted to take 100,000 by year, but I have put another zero here addition. So anyway, X, I'm going to consider around REXP, this number of observations with rate 1, and Y also I'm going to take the same number, thereby I can consider them as X column and Y column. Each row is a pair. So for each pair, I look at the situations where y is greater than x plus 2. Right? So then for those values, some of the values will be true, some of the values will be false. Right? So when say y greater than x plus 2, uh, that will be creating another column where some of the values are trues, some of the values are false. So when you take the mean of that column, you get the sum of the truths divided by the now total number of observations, which is equal to n. So that's what I get. That is actually the proportion of times this condition is satisfied. So that I got as 0.067 as the approximate value using the simulation. The theoretical value was 0.0676, or you can take it as 0.677. So in this case also it's 0.676. It's pretty accurate. So that is the answer for that question. Then connected to this independence, there are some other corollaries, but I am mentioning them as theories. If x and y are independent random variables, then any functions of those random variables are also independent. Actually, this is a very intuitive theorem, because if x and y are independent, then say any function g of x and g of y, h of y, for example, must also be independent, right? Because if x, the y value of y, when you're observing x and y, say pairwise, for example, if the y value doesn't depend on x, then the g of x doesn't depend on g of y, or g of y doesn't depend, h of, it can be another function, h of y. H of y doesn't depend on g of x also, right? So it's intuitively correct, and we can prove it for a particular case I have proved here, assuming that g and h, two functions, say strictly increasing functions taking, but this will be correct for any other type of functions also. But here I'm just considering a particular case. Suppose g and h are increasing functions, so then easily we can prove it. So what we want to look at is the cumulative distribution function. It's easy to look at in this case, right? Uh, because we have not discussed how to get the density function of g of x and h of y still. Therefore, we look at the cumulative. We can go by the definition in that case. So let's look at the cumulative distribution function of gx and hy evaluated at some point x and y. So that's going to be by definition probability gx less than or equal to simple x, hy less than or equal to simple y. Notice here g of x here capital, h of y here y is capital. Simple xy are some real numbers. And this can be written as probability x less than or equal to g plus x, and y less than or equal to h inverse y, you can consider this inverse because we are considering strictly increasing functions. And then because uh, x and y are independent, right? So this is probability x less than or equal to some value, say x dash. This is y less than or equal to some value, say y dash, right? So what you have here is actually the joint cumulative distribution function of x and y evaluated at this value and this value. But because x and y are independent, that will be equal to the product of marginal cumulative distribution functions, right? So which is equal to here probability x less than or equal to g of inverse g inverse x times probability y less than or equal to h inverse x is the same as g of x less than or equal to simple x probability times the probability h of y less than or equal to simple y, which is equal to this expression. So therefore, it shows that the cumulative distribution function, joint cumulative distribution function of gx and hy is equal to the product of individual marginal cumulative distribution functions of gx and hy respectively. So that, according to the definition of the independence, show that gx and hy are independent. So this is only a particular case, but you can prove it for general cases as well. Right. So now we will look at a particular function, some other particular function. If x and y are independent random variables, then expected value of, right here, earlier we were looking at densities and cumulative distribution functions. Here we are now applying independence for the expected value. If x and y are independent random variables, expected value of x and y should be equal to expected value of x times expected value of y. This is a very useful result. Of course, this can be applied only if x and y are independent. So let's try to prove this thing using the previous definition. So expected value of x times y. So this function of this like g of xy, right? So we are finding the expected value of g of xy. So by definition, it's going to be g of xy times the joint density integration with respect to x and y. So you can, I have, well, this is the same as, yeah, this line is actually now because x and y are independent, you can write down this joint density as the product of uh, the densities, individual densities x and y. So that's coming from the independence of, because we are assuming that x and y are independent, right? So when x and y are independent, this joint density can be written as the product of individual densities. So now when you are integrating this x and fxx can be taken as one part, y and fyy can take as another part, and therefore, because they individually contain, one part contains only x, the other part contains only y, therefore this double integration can be written as the product of two integrations like that. One is a function containing x's only, the other one is containing y's only. So this one is by definition the expected value of x. This is by definition of expected value of y. Right. So that's an important result. Another important result comes when x and y are independent for the moment generating function, for the joint moment generating function. The joint moment generating function, no, sorry, we will talk about the joint moment generating function. In that case, the joint moment generating function will be denoted by m, x, comma, y, t1, t2. That's how we will define the joint moment generating function. Here, what we are looking at the moment generating function of one variable. That variable is x plus y. Right? Suppose you have two independent random variables, x and y. You are interested in x plus y. So if we find the moment generating function of x plus y evaluated at t, we can show that that is equal to the moment generating function x evaluated at t times the moment generating function of y evaluated at t. Right? So this is again a very useful result, especially when you are finding the distribution of sum of IID random variables or sum of independent random variables. They may even not be identically distributed as long as they are independent. When you are finding the distribution of the sum of several random variables, this result is very important to get the moment generating function of the sum. Right. So let's prove this one also. So let's look at the moment generating function of x plus y evaluated at t. By definition, it's equal to the expected value of e to the power capital X plus y times simple t. And that can be written as expected value of e to the power xt times expected value of yt. Right. So now this thing, for example, is like a w. This may be something like u, where this is a function of x only, this is a function of y only, right? So these two functions separately, these are functions of independent random variables, right? So therefore, this quantity and this quantity will be independent, right? As in the previous case, I told you that if x and y are independent, then gx and hy are independent. So this is like a gx and this is like hy because x and y are independent. This is independent of this one. So therefore, from the previous result about the expected value of some function of x times another function of x should be equal to, because they are independent, expected value of this quantity times this quantity, right? So that is, so by definition then this is equal to m. So I have to put a bracket here as usual. Not put, because in the book, actually, your book, you don't have this bracket, but it's better to put the bracket, right? Just to, so that is the expected value of this quantity. But this is the moment generating function. Once you put the bracket, that is the expected value of e to the power xt, which is the moment generating function of x evaluated at t, and similarly, is the moment generating function of y evaluated at t. That's so that gives you the result that we wanted to prove. And then finally, we are going to look at the expression for the variance of the sum of two random variables when x and y are independent, right? So variance of the sum of independent random variables. If x and y are independent, then variance of x plus y is equal to variance of x plus variance of y. Right? If they are not independent, there will be another term coming that will be 2 times the covariance between x and y. But if x and y are independent, then the covariance term will be 0. Therefore, variance of x plus variance of y will be variance of x plus variance of y if x and y are independent. So we can prove it very easily using the definition of the variance of x plus y. Right. So in order to make the quantity simplify, let's take expected value of x to be mu x and expected value of y to be mu y. Then the variance of x plus y is equal to by definition. And then of course, then if expected value of x plus y will be equal to mu x plus mu y. Right. So the variance is, of some quantity, let's say, for example, this is Z, variance of Z is equal to expected value of Z minus the expected value of Z square, right? So let me write down here because it's, I have ignored one line before this. So before this, there will be a term like this. So this has to be expected value of x plus y minus mu x plus mu y, and then so this, I'll put that bracket here, square, and then this, right? So the random variable minus the mean of that square. So that is what you have here, but you can, we are considering x minus mu x plus y minus mu y square. So that is the same as this. And then if you expand this, you have expected value outside, then square of this quantity, and then square of this quantity, and then twice the expected. You can put the expected value with each quantity. That's the property of expected value. Expected value of a sum is equal to sum of the expected values. So you will get this expression, right? Now, because x and y are independent, you can see that this is a function of x only, this is a function of y only. So expected value of this quantity will be equal to then expected value of x minus mu x times expected value of y minus mu y, right? That's coming from the previous theorem. But now expected value of x minus mu x will be 0. This is also 0. Therefore, this whole thing will be 0. So therefore, what you are going to left with is this quantity and this one. But that is the variance of x. This is the variance of y. So finally, you get this expression. So that is the end of this session. Uh, so in the whole lecture, I started with the uh, definition of joint cumulative distribution functions, and then we discuss marginal cumulative distribution functions, and then joint uh, probability mass function and marginal mass functions, and then joint density, marginal density. Um, so let me go back to the first. So these are the quantities that we discuss throughout these three parts of the lecture, right? Joint and marginal. We look at some expressions, and then we solve some problems, right? An important thing is that when you are integrating uh, correctly, you have to choose the limits of the integration. So that is an important thing to understand. After those quantities, we look at the independence, the expected value, and then independence, right? Uh, and from that, we looked at some important theorems regarding the expected value for the product of two terms, and then the moment generating function of the sum of two independent random variables and the variance of the sum of two independent random variables. So that's the end of this lecture. In the next lecture, I will start with some problems, discussion of some problems, and then continue from there. So in those problems, we will be using again the ideas we discussed in this lecture.